Ayubowan everyone, and a very warm welcome to Study Hub Sri Lanka. Today, we're diving into a really important topic for your A-level physics exam, elasticity. We're going to break down everything you need to know, from the basic ideas all the way to the stuff that shows up in your papers. So let's get started.
So think about this for a second. We've all done it, right? You take a rubber band, you stretch it out, you let it go, and it just snaps right back to its original size. Or a spring. Why does that happen? What's the physics going on there that gives it that incredible bounce-back ability? Well, that special property is what we call elasticity, and that's exactly what we're going to explore today. Okay, so here's the official definition for you. Elasticity is simply a material's ability to go back to its original shape and size once you stop pulling or squashing it, after that deforming force is gone. A little stretch is what we call elastic deformation. It bounces back, no problem. But if you pull it too hard, you cross a line called the elastic limit. After that, you get plastic deformation, and that change is permanent. It's not going back to the way it was. Now, to properly understand and, more importantly, to measure elasticity, we need to get our heads around two absolutely key ideas: stress and strain. The easiest way to remember them is like this. Stress is the cause. It's the force happening inside the material. And strain is the effect. It's the stretch or change in shape that we can actually see. Let's break each of those down. Let's dig in a little deeper here. Imagine you're pulling on a wire. The particles inside that wire are actually pulling back, trying to resist you. That internal fight, that restoring force spread over the wire's area, that's what we call stress. It's what the material is feeling on the inside. Now, strain, that's the result we see on the outside. It's the change in length compared to its original length. It's what we can physically measure. So the formula for stress is pretty simple, actually. It's just the force you apply, F, divided by the cross-sectional area, A. And the unit we use is newtons per square meter, which you'll probably recognize as pascals. Yep, the same unit we use for pressure. The really important thing to get here is that if you apply the same force to a thin wire and a thick wire, the thin wire experiences way more stress because that force is concentrated in a much smaller area. And strain is even easier to understand. It's just the extension, how much it's stretched, which we call E, divided by the original length of the material, L. Now notice something cool here. You're dividing a length, say in meters, by another length in meters. So what happens to the units? They cancel out. That means strain is just a pure number, a ratio. So if you get a strain of, say, 0.1, it just means the material has stretched by 10% of its original length. Simple as that. Okay, so we've got stress, the cause, and strain, the effect. The big question is, how do these two relate to each other? Well, way back in the 17th century, a scientist named Robert Hooke figured this out. He discovered a beautifully simple rule that is the absolute foundation of this topic, and you will 100% need to know it for your exams. And this is it, Hooke's law. What it says is that as long as you don't stretch something too much, that's the within the limit of proportionality part, the force you apply is directly proportional to the extension you get. In other words, if you double the force, you're going to get double the stretch. Triple the force, you get triple the stretch. It's a really clean, predictable relationship. And this graph is the perfect picture of Hooke's law. You see that beautiful straight line going right through the origin? That's what directly proportional looks like. You've got force on the y-axis and extension on the x-axis. The slope of this line, how steep it is, actually tells you how stiff the material is. A really steep line means you need a lot of force for just a little bit of stretch, so it's a very stiff material. Now, Hooke's law is great for describing one specific spring or wire, but how do we compare the stiffness of materials themselves? Like, how can we say for sure that steel is stiffer than copper? With a number. For that, we need a special constant that's unique to each material, and that constant is called Young's modulus. And the definition of Young's modulus is so neat. It's just the ratio of stress to strain. That's it. By doing this, by dividing stress by strain, we get a single number, which we call Y, that tells us the inherent stiffness of a material, completely independent of its shape or how big it is. It basically tells us how much stress you need to apply to get a certain amount of strain. This table really shows you what I mean. Just look at the numbers. Steel has a Young's modulus of 2.0 times 10 to the power of 11 pascals. That's a massive number. Now compare that to aluminum, which is down at 0.7. That tells you that steel is almost 3 times stiffer than aluminum. It takes so much more stress to get it to deform. And this single number is why we use steel for things like bridges that have to be super rigid. and aluminum for things like airplanes, where you need something lighter and a bit more flexible. Okay, now let's put all of these ideas together and look at what is probably the most important graph in this whole topic, the stress-strain curve. You can think of this graph as the complete life story of a material as you pull it apart, right from the first tiny stretch all the way to the point where it breaks. Understanding this graph is absolutely essential, so let's walk through it step by step. So let's follow this journey. Starting from the origin, O, up to point A, we've got that straight line. This is our Hooke's law region, where everything is perfectly elastic. Even past A, up to point B, the elastic limit, if you let go, it'll still snap back. But once you pull past point C, the yield point, that's the point of no return. You've entered the plastic region, and any stretching you do now is permanent. Point D is the ultimate tensile strength. That's the absolute maximum stress the material can take. After that, it starts to get thin in one spot, what we call necking, and then finally, at point E, it fractures, it breaks. All right, let's do a quick fire review of the absolute must-knows for your exam. Ready? Stress is force divided by area. Strain is extension divided by original length. Young's modulus is stress divided by strain. It's the measure of stiffness. And Hooke's law says force is proportional to extension, as long as you're in the elastic region. Those are the big four. Lock them in. And to leave you with a final thought to chew on, we've only really talked about stress from pulling on things. But what about temperature? Think about a huge steel bridge on a really hot day. The steel wants to expand, right? But it's bolted down at both ends. It can't go anywhere. So what kind of stress is building up inside that bridge, even with no cars on it? That's a concept called thermal stress, and it's a perfect example of how all these ideas apply in the real world. Thanks for joining us here on Study Hub Sri Lanka. Study well, and we'll meet again with another episode for your science subjects.